Swayam Prabha. Digital India. Educated India.
Hello all, welcome back. In the previous two lectures, we were discussing about synthetic unit hydrographs. For the ungauged catchments, for carrying out hydrologic studies, we can make use of the data or unit hydrograph which is derived for the neighboring gauge catchment. The condition is that the gauge catchment should be hydrologically and climatically similar to that of the ungauged catchment. Two different types of synthetic hydrographs which we have covered are Snyder's synthetic unit hydrograph and SES dimensionless synthetic unit hydrograph. Today, let us solve some numerical examples related to these synthetic unit hydrographs. First one is related to Snyder's method. The first example is watershed A having the 10-hour unit hydrograph derived from the observed rainfall and runoff of an isolated storm on it has the following characteristics. Basin lag 35 hours, peak discharge 150 meter cube per second, area of the watershed 3000 kilometer square, length of the main stream 150 kilometers and length of the stream from a point near to the centroid to the outlet point is 75 kilometers. Watershed B, which is hydrologically similar to watershed A, has the following characteristics: area 2000 kilometers square, L 100 kilometers and LC 75 kilometers. Determine the 5-hour synthetic unit hydrograph for watershed B using Snyder's method. We know in the case of Snyder's synthetic unit hydrograph, the relationships between the geomorphologic characteristics and hydrograph characteristics were found out. So, here in this case the geomorphologic characteristics given are the area of the catchment 3000, L 150 and LC 75 kilometers in the case of watershed A, and in the case of watershed B, which is ungauged catchment, is having area 2000 kilometers square, L 100 kilometers and LC 75 kilometers. So, we need to derive the synthetic unit hydrograph for the ungauged catchment B by making use of the data from the gauged catchment. For the gauge catchment, there will be rainfall runoff data available, that is the effective rainfall and the corresponding stream flow data will be available, and from that unit hydrograph can be derived. That step we do not have to carry out here because we have been given the hydrograph characteristics of the gauged catchment here, that is the basin lag and peak discharge. Now, let us start solving the problem. Data given we have already seen. For the watershed A is the gauged catchment. So, for that the hydrograph which is given to us, that is the details which are given to us, is from the derived unit hydrograph. For the gauge catchment, the unit hydrograph, if we have to derive or it is already available, that is termed as the derived unit hydrograph. The characteristics of the derived unit hydrograph is given, that is the effective rainfall duration TNR is 10 hours, basin lag TNPR 35 hours, peak discharge 150 meter cube per second, and the geomorphological characteristics are given to us. Now, we need to make use of this data for deriving the synthetic unit hydrograph for ungauged catchment. So, the synthetic unit hydrograph which we are going to derive for the ungauged catchment is the required unit hydrograph. So, watershed B, we need to derive the required hydrograph. Area LLC of the ungauged catchment is given to us. We need to derive the unit hydrograph having duration of effective rainfall 5 hours. We need to derive the 5-hour unit hydrograph for the ungauged catchment. In these type of problems, the first step is to check whether the derived unit hydrograph or the unit hydrograph of the gauge catchment is a standard unit hydrograph or not. So, first let us check whether the derived unit hydrograph of watershed A is a standard UH or not. How can we check that? We know the condition for that. For a standard unit hydrograph, the basin lag is given by 5.5 times the duration of the effective rainfall. So, the equation is Tp should be equal to 5.5 times Tr. Tr is the duration of the effective rainfall and Tp is the basin lag. For the derived unit hydrograph, TNPR is 35 hours and TNR is 10 hours. I am putting a notation N for the derived unit hydrograph, which is known data or the given data. Now, we can check whether this UH is a standard UH or not. So, we can calculate 5.5 times TNR, 5.5 into 10. 10 hours is the duration of effective rainfall, or the 10-hour unit hydrograph is the derived unit hydrograph. So, that is coming out to be 55 hours. We are having 5.5 times TNR as 55 hours and TNPR as 35 hours. So much of difference is there. So, from that we can understand that the derived unit hydrograph or the known unit hydrograph for the gauged catchment A is not a standard unit hydrograph. So, TNPR is not equal to 5.5 TNR. So, this is not a standard unit hydrograph. Then we have to go for redefining the basin lag. So, basin lag Tp for watershed A can be calculated by the formula given by Snyder. This is the formula for the basin lag for the unit hydrographs which are not standard UH. Tp is given by TNPR plus Tr minus TNR divided by 4. Since we are assuming that this is a standard unit hydrograph, this Tr should be equal to Tp divided by 5.5. So, we can substitute that Tr is equal to Tp divided by 5.5 and this equation can be modified as Tp is equal to 22 divided by 21 TNPR minus TNR divided by 4. TNPR we know, TNR also we know, it is already given to us related to derived unit hydrograph. This can be calculated as 34.048 hours. We have found that the unit hydrograph of the gauge catchment is not a standard UH. So, the basin lag is redefined by the formula given by Snyder and the value is calculated to be 34.048 hours. Now, we will be making use of this basin lag for the consequent steps. Next step is to estimate the coefficients Ct and Cp using the data of watershed A. We have to make use of the data corresponding to watershed A and the formula for Ct is given by Tp divided by 0.75 LLC to the power of 0.3. Tp should be the value which we have calculated based on the modified formula, that is 34.048 hours. That we can substitute here and also L and LC for watershed A. So, once we substitute these values, we can calculate CT as 2.765. Now, coming to CP, the formula is QNPR TP divided by 2.78. QNPR we do not have, actually this Q, small q is the discharge divided by area of the catchment. We have been given the peak discharge, we do not have the value of the small q that we need to calculate, that is capital Q divided by the catchment area. Area is 3000 kilometer square. So, we can calculate QNPR as 150 divided by 3000. Peak discharge is 150 meter cube per second. That can be calculated as 50 into 10 to the power of minus 3 meter cube per second kilometer square. Meter cube per second value, that is capital Q value, is divided by the area of the catchment. So, we got the value corresponding to QNPR. Now, we can substitute here in order to calculate CP. So, CP can be calculated as 0.612. Now, we are with the coefficients CT and CP. These two coefficients, which are derived from the properties of the gauge catchment, can be utilized for deriving the hydrograph characteristics of the ungauged catchment. Now, we are moving on to next step related to watershed B, that is the derivation of required unit hydrograph. The synthetic unit hydrograph which needs to be derived is for the ungauged catchment, that is termed as the required unit hydrograph. And watershed B is having these characteristics: area, length of the mainstream, LC, we know already, and we need to derive a unit hydrograph from an effective rainfall having a duration of 5 hours. So, here we are going to derive 5 hour synthetic unit hydrograph. The values for CT and CP we have already found out. These values can be utilized here. So, first we will calculate the basin lag. How can we calculate basin lag? The formula is TPR is equal to 0.75 CT LLC to the power of 0.3. The same formula which is used for calculating CT in the case of gauge catchment is utilized here. Now, we know the value of CT, that can be substituted over here to calculate the basin lag of the synthetic unit hydrograph of the ungauged catchment. TPR is given by 0.75 CT LLC to the power of 0.3. Here we are going to substitute L and LC values of the watershed B, for which we need to derive the synthetic unit hydrograph. CT value is 2.765. So, we can calculate TPR, that is the basin lag, as 30.148 hours. The basin lag which is calculated for the ungauged catchment is 30.148 hours. Now, next step is to check whether this unit hydrograph which is having a basin lag of this much value is corresponding to a standard unit hydrograph. If it is a standard unit hydrograph, it should follow the relationship Tp is equal to 5.5 Tr. Our synthetic unit hydrograph, that is the required unit hydrograph, is of duration 5 hours. So, we are having already the value corresponding to duration of the effective rainfall, that is 5 hours. Now, we have calculated the basin lag also. Now, we need to find out whether this hydrograph is corresponding to a standard unit hydrograph. We can check that Tr should be equal to Tpr divided by 5.5. So, 30.148 divided by 5.5 will be giving you a value 5.48 hours, but the required duration is 5 hours. So, the effective rainfall duration for which the synthetic unit hydrograph has to be derived is 5 hours, and the duration of the standard unit hydrograph for the ungauged catchment is 5.48 hours. So, definitely we need to redefine the basin lag by using the formula suggested by Snyder, as we have done in the case of unit hydrograph of the gauged catchment. So, we can modify that. So, here I am putting a notation TR dash as 5 hours. In order to avoid confusion, I have put a prime notation here. TR dash is 5 hours, do not get confused, it is the duration of the effective rainfall. We can redefine the basin lag by using the formula T dash PR is equal to TPR minus TR dash divided by 4. So, here we can substitute the corresponding values. TPR is 30.148 and TR is 5.48 and TR dash is the duration of the required unit hydrograph. So, this value is calculated as 30.028 hours. Now, for making the synthetic unit hydrograph to be a standard unit hydrograph, we have recalculated the basin lag. That is found out to be 30.028 hours. So, now the 5-hour effective rainfall duration and the corresponding basin lag is standing for the standard unit hydrograph. Next step is to calculate the peak discharge per area, that is small QP. Small QP is given by the formula 2.78 Cp divided by TPR. Cp value is already here 0.612. This can be calculated as 0.05643 meter cube per second kilometer square. You look at this equation, in the denominator we are having the value corresponding to TPR. This TPR I have substituted 30.148, that is from the calculation which we have done before making it as a standard unit hydrograph. If you want to substitute it as the basin lag of the standard unit hydrograph, that is also possible, but according to Snyder there is another formula given to calculate QP. So, when it comes there we will be substituting the duration of standard unit hydrograph. Even if you are substituting here, you will get the correct answer, because there we are multiplying with a time factor. There this value get cancelled. So, you will be getting the same answer whether you are substituting here as the TPR dash value or there according to the formula given by Snyder. So, according to Snyder's formula, I have followed the steps. So, QP is calculated to be 0.05643. Now, we are going to make use of the formula provided by Snyder for finding out peak runoff per unit area for the required synthetic unit hydrograph. So, that is QPR is equal to QP TPR by T dash PR. This is the factor which I was talking about, that is TPR divided by T dash PR. So, here that TPR which we have divided over there in the previous step is getting cancelled, and in effect what we are doing, QP divided by that particular TPR dash which we have calculated. Here we can substitute the corresponding values. QP is equal to 0.05643 and TPR is 30.148 and T dash PR is 30.028. This is the basin lag corresponding to standard unit hydrograph. The value is calculated as 0.0567 meter cube per second kilometer square. Next is time base for the required synthetic unit hydrograph. For that also we are having the formula TB is given by 5.56 divided by QPR. So, here for QPR we can substitute this value, that is equal to 5.56 divided by 0.0567, it is coming out to be 98.06 hours. So, here we are with the QPR value and also time base value. Here we have calculated the peak discharge per unit area. We need to get the value corresponding to peak discharge, that is capital QP. Capital QP can be obtained by multiplying QPR with the catchment area. Catchment B is having an area of 2000 kilometer square. So, this can be calculated as 113.4 meter cube per second. Now, two more parameters we need to find out. According to Snyder, two other factors which are required for deriving the synthetic unit hydrographs were the widths corresponding to 50% of the peak discharge and 75% of the peak discharge. So, widths of Snyder's synthetic unit hydrograph W75 and W50 we need to calculate. Only the difference is in the coefficients 1.22 and 2.14, otherwise the formula is same. So, once we substitute here in these equations the value corresponding to QPR, we can calculate W75 as 27.07 and W50 as 47.48. So, now we have completed the calculations related to the required parameters for deriving synthetic unit hydrograph. Next step is to plot the synthetic unit hydrograph. Now we can start plotting the graph. We are having discharge along the y-axis and time along the x-axis. The synthetic unit hydrograph which we are going to draw is corresponding to an effective rainfall having a duration 5 hours. So, this is the effective rainfall pulse having duration TR is equal to 5 hours. For that we have derived the different parameters. Now, let me describe different terms which are required for drawing the synthetic unit hydrograph. Beginning of synthetic unit hydrograph, 50% rising. 50% rising is the rising limb up to 50% of peak discharge, and 75% is the rising limb starting from 0 to the 75% of the peak discharge. Peak you already know. In the similar way 75% of falling and 50% of falling, and at the end we will have the ending of the synthetic unit hydrograph, that is corresponding to TB, base time of the unit hydrograph. So, that base time can be marked first. How much is the base time corresponding to the unit hydrograph? This we have calculated. That can be marked over the figure. Next is TP, time to peak. We were discussing about basing lag, small TP, but here plotting the synthetic unit hydrograph we need to have the value corresponding to time to peak. How can we calculate that time to peak? When we were discussing about basing lag, it is the difference between the times corresponding to the centroid of the effective rainfall and the peak of the hydrograph. The time to peak can be marked like this, but we do not have the value corresponding to time to peak. We are having the value corresponding to basin lag only. So, if basin lag is there with us, how can we calculate the time to peak? Time to peak can be calculated by taking the sum of TR by 2 and TPR, basin lag plus 1/2 of the effective duration of the rainfall. TR in our case is 5 hours and TPR we have already calculated. Based on that we will get the value corresponding to TP. We can draw a line through TP like this, and corresponding to that the discharge value is QP. So, this point is corresponding to TP QP. So, we have determined the point corresponding to the peak discharge in the synthetic unit hydrograph. After that what we will do, we will mark the point corresponding to 50% of peak discharge and 75% of peak discharge. Now, corresponding to 50% peak discharge and 75% peak discharge, we know the discharge values, but we need to get the time value corresponding to that. For that what we will do? We have already found out W50 and W75. According to Snyder, 1/3 of these widths should happen before the peak. That way we need to locate the time corresponding to 50% rising and 75% rising. So, corresponding to 75% rising, it will be TP minus W75 by 3, that is 1/3 of that width will be happening prior to the peak discharge. That we can mark over here in the figure. So, 1/3 of W75 will be marked here. In the similar way, for 50% rising also, 1/3 of W50 coming before the peak. So, the time corresponding to that 50% rising is TP minus W50 by 3. So, this is corresponding to TP minus W50 50 divided by 3. So, this value will be equal to 1/3 of W50. Now, in the similar way on the other side corresponding to 75% falling, it will be 2/3 of the width. 1/3 has happened before the prior to the peak and 2/3 will be happening after the peak has occurred. So, it will be Tp plus 2W75 by 3 and Tp plus 2W50 by 3. So, that we can mark over here like this. This is corresponding to 2/3 of W75 and below corresponding to 50% peak discharge, it will be 2/3 of W50. So, that way the total will be W75, 1/3 of W75 plus 2/3 of W75, it will be total W75. Now, we can move on to plotting the synthetic unit hydrograph. So, this way we can plot the synthetic unit hydrograph by connecting these points corresponding to W75, W50 and peak discharge. Now, we have seen how to plot the synthetic unit hydrograph based on the data from the known unit hydrograph from the gauge catchment. So, we can complete this with the values from the numerical example. So, we need to calculate the value corresponding to time to peak. Time to peak is calculated by using the effective rainfall duration and the basin lag. Effective rainfall duration is 5 hours and TPR is 30.028. Based on that, the value of TP is coming out to be 32.528. Now, by making use of this TP, we can calculate the time corresponding to 50% rising and all other time corresponding to 75% rising, 75% falling and 50% falling. So, these are the times corresponding to each discharges. Now, we need to calculate the values corresponding to peak discharge. The values corresponding to peak discharge we have already calculated. We just have to take those values for plotting the synthetic unit hydrograph, that is Q peak and 75% of Q peak and 50% of Q peak. So, those values are given over here in this column. So, the ordinates of synthetic unit hydrographs are corresponding to QP, 75% of QP and 50% of QP. Now, we can start plotting the synthetic unit hydrograph. So, the synthetic unit hydrograph can be plotted as shown in this figure. In this way, we can derive the synthetic unit hydrograph based on Snyder's method. Now, let us move on to the second method, that is based on SES dimensionless synthetic unit hydrograph. In the case of SES dimensionless synthetic unit hydrograph, dimensionless unit hydrograph and the corresponding ordinates have been given by SES after conducting so many studies in different watersheds. So, those dimensionless ordinates we will be utilizing here for deriving the synthetic unit hydrograph for our ungauged catchment. So, the next example is related to unit hydrograph derivation using SES dimensionless technique. Derive a 30 minutes SES dimensionless unit hydrograph for a catchment having drainage area of 50 km square, for which the time of concentration is 5 hours. Here in this case, we need to have the time of concentration. Time of concentration is given to us as 5 hours and area of the catchment 50 km square, and we need to derive 30 minutes synthetic unit hydrograph. Data given are catchment area 50 km square, time of concentration 5 hours. The effective duration of the rainfall is 30 minutes, that is 0.5 hours. The time of concentration is given to us as Tc is equal to 5 hours. In the case of SES dimensionless synthetic unit hydrograph, we were approximating the unit hydrograph in the triangular form. This is the SES triangular unit hydrograph, which we have already discussed while discussing the theory related to it. In the same way, we will approximate the unit hydrograph for this catchment also. That is, we will derive the triangular unit hydrograph first. After that, we will go for deriving the synthetic unit hydrograph by making use of the dimensionless synthetic unit hydrograph provided by SES. So, here we can calculate the time of rise, that is time to peak. How can we calculate? Here we have marked the TP, that is basin lag, TR is the duration of effective rainfall, capital TP is the time to peak or time of rising, that is from the 0th ordinate to the peak discharge where it is happening, that much time is TP. How can we calculate that? Here we are having the basin lag and also duration of the effective rainfall. So, we can calculate TP, that is the time of rise, as TP is equal to TR divided by 2 plus 0.6 Tc. Actually, TP is given by, time to peak is given by TR divided by 2 plus TP, small TP, basin lag. So, this basin lag approximated by 0.6 Tc. From the experimental studies, it is found that basin lag is approximately equal to 0.6 times the time of concentration. So, if TP is 0.6 times time of concentration, that plus half of the effective duration will be giving us the time to peak or time of rising. Now, by making use of this, that is TR is known to us, TC is known to us, we can calculate the time to peak or time of rise, that is coming out to be 3.25 hours. So, here in this case we have found out the time corresponding to the point where the peak is coming, point corresponding to x value, that is time value is calculated corresponding to the peak discharge. Now, for completing the triangular unit hydrograph, what else we need? We need to have the value corresponding to TB, that is the time base of the unit hydrograph. And for TB also, formula is given to us, that is based on the principle of mass curve we have seen. TB can be calculated by using the formula 2.67 TP. TP is 3.25 hours. So, TB is coming out to be 8.68 hours. Now, we are having the time base of the unit hydrograph and also TP, time of rising also there with us. Next value which is required for completing the triangular unit hydrograph is peak discharge. With these three values, time to peak, time base and the peak discharge, we can derive the approximate triangular unit hydrograph. So, the peak discharge QP is given by 2.08 A divided by TP. Area of the catchment is given to us. So, this can be calculated as 32 meter cube per second. So, all the values corresponding to a triangular unit hydrograph is here with us. We can plot the triangular unit hydrograph. Now, by making use of this data and the data from the SES dimensionless unit hydrograph, we need to derive the synthetic unit hydrograph. So, these are the data corresponding to dimensionless synthetic unit hydrograph proposed by SES, and the SES dimensionless unit hydrograph is plotted over here, and along the y axis we are having dimensionless discharge Q by QP, and along the x axis we are having the dimensionless time T divided by TP, and corresponding to T by TP and Q by QP we are having the values listed over here in the table. So, we already have the value corresponding to TP and QP. Once we multiply T by TP with time of rising, we will get the corresponding time, and corresponding value of discharge Q we will get by multiplying Q by QP with QP. So, that is what we are going to do here. We are having the value corresponding to QP and TP, that is from the triangular unit hydrograph. Once we multiply QP and TP with the values given over here in these columns, we can get the time in hours and the Q discharge in meter cube per second. So, by making use of the dimensionless synthetic unit hydrograph ordinates, we have found out the ordinates corresponding to the synthetic unit hydrograph for the ungauged catchments, for which we need to derive with the data given in the question. So, SES triangular unit hydrograph ordinates we have already computed, TP, QP and TB. Now, we can plot the synthetic unit hydrograph. So, these are the synthetic unit hydrograph. Red one is representing the SES triangular unit hydrograph and the blue one is representing the SES synthetic unit hydrograph. So, this is very simple by making use of the data provided by SES, that is for the SES dimensionless synthetic unit hydrograph curve, and also the corresponding data are given in all the textbooks which are explaining this topic, and by making use of those data and we are calculating the values corresponding to QP, TP. TP is not the small TP, that is not the basin lag, it is the time of rising or time to peak, and the time base of the unit hydrograph we can get the triangular unit hydrograph, and by making use of those values along with the dimensionless ordinates from SES dimensionless synthetic unit hydrograph we can derive the SES synthetic unit hydrograph for the ungauged catchment. So, these are the two types of synthetic unit hydrographs we have covered, that is Snyder's synthetic unit hydrograph, which is derived based on the morphological characteristics and the hydrograph characteristics, and second one is the synthetic unit hydrograph proposed by SES, that is SES dimensionless synthetic unit hydrograph is utilized for deriving SES synthetic unit hydrograph. Now, corresponding to this topic, more examples and exercise problems can be seen in these textbooks. Try to solve different numerical questions for making the concepts clear. So, here I am winding up the numerical problem solving related to synthetic unit hydrograph. Thank you.